When it comes to deep learning, one theme became apparent. Data matters. However, what do we do if we do not have enough labeled data? Well, there is one thing we can do. We can use unsupervised machine learning. Welcome back to the Applied Deep Learning course. In today's lecture, we're going to take a look at autoencoders and generative adversarial networks and see how we can do unsupervised machine learning with those techniques to help us if we have a lack of labeled data. But before we do that, let's have a quick recap on what we talked about last week. On what data does reinforcement learning operate? We've seen supervised learning where we have our inputs and targets. We have seen unsupervised learning where we only have some data, and reinforcement learning, in contrast to that, operates on state-action pairs. What are some of the unique challenges for reinforcement learning? I'm just going to name a few, something like delayed consequences or exploration, where we might have censored data, and of course all of the optimization and generalization challenges that we already saw in other parts of deep learning. But especially delayed consequences is particularly challenging for reinforcement learning, as we might only know whether an action was good or not long after we took that action. What do the quality function, value function, and policy function compute? The quality function says, well, it's the expected total reward when we're in state S and we take an action A. So how good is that action A gonna be in my current state S into the future? That's the quality function. The value function says, if I am in state S, whatever that may be, how good is that state in general without referring to a specific action? And the policy function is the function that computes the probability of the action A being the best action to take in our state S. So it's basically saying, you're here, go there. Given a quality function, how can we obtain a policy function? So there are many ways how we could do it. The easiest way, and something that makes a lot of sense, is that we take the argmax of that action that gives us the highest expected reward into the future. So we have a quality function and we're in state S, and we can compute for all different actions A how much rewards we are going to get, and we simply take that action that shows that the quality function tells us would give us the highest reward into the future. And what was the main idea behind hindsight experience replay? So when we have a scenario where our rewards are on this sparse and where it's hard for the agent to get meaningful feedback, we can artificially create a dense reward setting by replacing the actual goal with a virtual goal. So the action performed by the agent was not the right action, so it wouldn't get any reward. But if we then, after the agent has taken that action, swap the goal and say, well, it was what I intended to do, then we can give him a positive reward for that. And the side effect is that it will actually learn to do that action that it misdid, so to speak, in the previous step from his failure. And we're kind of, if it ever has to take that action in the future or to achieve that goal, it already saw it once. So imagine that you have a robot that learns to put objects into boxes. Say you have 10 boxes in front of you and you wanted to put the object into the first box. So if it correctly puts the object in the first box, well, congratulations, you can give it a reward. However, if it falls into the second box, it's not what it was intended to do. But still, you can say, okay, if I wanted the agent to put the object into the second box, well, it did the right thing. So now you trained the agent to learn how to put objects into the second box. If the agent completely throws the object off the table, you can still penalize the agent for that. But at least for these 10 boxes that you have in front of you, putting objects into these boxes, you can, with hindsight experience replay, create a more dense reward scheme for your agent. Now to today's topic, autoencoders. A neural network that we train to copy the input to the output is what we call an autoencoder. Sounds a bit odd to start with. So what we have is, we have our input X, and we learn an encoding F to go from that X to a hidden representation, H. So that's our encoding function, and then we have a second part, which is a decoder that takes this representation H and decodes it into an output representation R. And now the goal would be that the reconstruction R should be as similar to the input X as possible. G of f of X should be X again, as close as possible, of course. And the way how we do this is we build a network and we kind of use appropriate building blocks for this, and we penalize the network whenever it produces something that does not look like the input. So we would call that a reconstruction loss, and it's basically a feed-forward network. So we go from X to H and then back to R, and then we compute what has gone wrong here. When you think about it, we take X, we compute something, and then go back to the same thing. Why would anyone want to do this? And it's a legitimate question to ask. So if we already know X, why would we want to do this and spend resources and efforts into getting something that we already have? Well, because we can, and besides, there are some really cool things that we can do with this basic idea. So what we usually have when we talk about autoencoders are so-called undercomplete autoencoders. So most of the time, the thing is that we're not interested in the reconstruction R, because we already have X. Therefore, we have to be interested in something else. What is the thing that we're interested in? Could be a couple of things. It could be the latent space representation, this thing in the middle, the encoding, but it could also be the function f or the function g. So typically what we have is, and by saying an undercomplete autoencoder, is a latent space dimension. So this h, how we represent our input in this neural network, in the middle of this network, have a much smaller dimensionality than the input. So if our input has 1024 inputs, our latent space could just have 4 neurons, 4 numbers to represent all of these inputs. And by forming this so-called bottleneck here in the middle, where we kind of have to flush all our input through, we force the network to learn an efficient and compact representation of our input. And this encoding H is what we're often interested in. One thing that we all have to be aware of here is that if we do an undercomplete autoencoder, whatever we will get back as an output will have a certain loss. So this is a lossy encoding, and whenever I hear lossy encoding, one thing that comes to my mind is MP3 or JPEG. You know, when we compress audio and images into a really small format where we can still store lots of information in there and we don't even hear it. Kind of the idea of this MP3 that humans don't perceive the loss of information. So they were designed in a clever way. And I think it's just a matter of time until maybe someone comes up with a clever alternative to MP3 or JPEG that they got from such an autoencoder scheme where they tried to compress images in a machine learning way and get back to the original image. And all you then have to do is not ship the algorithm, but ship those weights that were used here. And if you can do this in an efficient way, you might be able to save a lot of bandwidth because you can store images in a much denser way than you can do right now. One more thing to say here, if our encoding here is just a linear function, so we're not having any nonlinearities here, this scheme here would actually be would resemble the principal component analysis, PCA, where it would just learn to kind of take a look at the most important dimensions of our input space. There are a couple of things that you should keep in mind when talking about undercomplete autoencoders. So imagine that we have an autoencoder that has just a one-dimensional code. So we only get one value here in the center in our latent space, which could say a number 1, 2, 3, 4, 5. But a very, very powerful decoder. What would happen? Well, the decoder, so the neural network, would probably learn to memorize every single input sample. So if we have just a small latent space and an extremely powerful decoder, it could just memorize every single output or every single sample and just learn a mapping from that latent space to each particular sample. And obviously this is not what we want. So we have a bit of conflict here when you think about it. So on the one hand, we want this to be very good and have a lot of power and capacity. But on the other side, if we increase the capacity of this thing, or if we increase the latent space, well, we're not getting much of a reduction here. So it will be able to perfectly reproduce our input, but we're not gaining anything from this. So we have to kind of strike a balance here. So on the one hand side, we want models with high capacity, but on the other side, if we use a too high capacity here, we will overfit our training data. And the solution to this is, as we know, the regularization. Regularized autoencoders are actually preferable over autoencoders that have a smaller capacity, where we kind of just reduce the number of neurons. So how we can regularize an autoencoder could be, for example, that we add an additional loss. That's a good way. So if we incentivize our network to follow other objectives than just plainly reconstructing our input, we can kind of guide the network into doing something meaningful. And depending on whatever loss function we add or how we shape it, we can achieve different objectives and really make sure that our autoencoder has certain properties. So for a sparse autoencoder where we want to have a very small representation in our latent space, we can actually add a penalty if our representation H becomes too big. So say that we kind of measure the magnitude or something here, like this omega function that says if you use 10 neurons, you get a certain penalty. If you only use 2 neurons, you get a much lower penalty. You can kind of make sure that the network is forced to only use a small representation, and then you could kind of remove the last 8 neurons in the middle because it was kind of trained to only use the first 2 in there. Or you could add a completely different loss, a completely different objective like classification. So we have our latent representation, and from that latent representation we of course try to reconstruct our input, but at the same time we also want to do a prediction and say what object we're seeing. So we're doing classification and reconstruction at the same time. And as I said, adding these additional objectives can really help the network to learn and have certain properties. I already talked about this latent space. Let's talk a little bit more about it. So the space that our hidden variable h is in is again probably n-dimensional space, depending on the number of neurons that we have there. And it's the space of this code h. We want this latent space representation to have certain properties. One would be that it's compact. We don't want to overdo it there. We easily want to separate different classes. We want to be able to use that latent space representation. And ideally, we want something like an interpolate mechanism where we can say, I go from this point to that point, and by moving in our latent space, I can see how the object changes. And then ideally be able to interpret maybe the trajectory or interpret a certain axis that we say, okay, in my latent space, this variable reflects a certain property, and if I turn it on or off, my output will change in that particular way. In theory, we could build a stochastic encoder and decoder where we replace our function with conditional distributions. The problem is that in general, this is intractable. And to solve this intractability, there is a really clever extension to autoencoders, which is called variational autoencoders. In variational autoencoders, what we're doing is that we're kind of giving our autoencoder a probabilistic spin. And what we do is, instead of having just one layer or one output in our hidden representation with some values, we're actually splitting it up. And we're saying, okay, we're predicting two different things here. We say we split our hidden representation into a distribution, our hidden layer, our hidden values, into a probability distribution. And that probability distribution has to be described by the center mu and the variation sigma. And if we're predicting that mu and sigma, what we can do is we sample from that probability distribution, and then we apply our reconstruction function. So instead of having a deterministic hidden layer representation, we're saying we're having a distribution here. So instead of say, okay, we encode each value into our latent space, into one point in our latent space, we're mapping it onto kind of a probability distribution in our latent space. Means, of course, that whenever we run one sample through this, that we might get a slightly different output because we actually sample from this probability distribution here that we are learning. And the good thing about this is actually that the decoder now is forced to be able to handle slight variations, because each time, if you feed the same input in there, the decoder will see a very slight variation of that input, which is good because then it becomes more robust. So why would you want a variational autoencoder? One, because it gives us all of these nice properties that we want in our latent space, like it's being compact, it's continuous. It does allow us to random sample from that latent space and to interpolate between this. And additionally, what's really cool about this is that by using variational autoencoders, especially one type of variational autoencoders that we'll take a look at in a second, we can learn latent factors that really correspond to certain properties in our input and that we can then interpret in a really nice way. So here would be an example of our latent space representation, and some images that we generate out of this. We will see this in code a little bit later. What we can see here is the number 1 is this pale yellow in the left top corner. And when we go down to the class 2, which is somewhere at the middle, we can kind of move along our latent space representation, because there are just 2 points in this 2-dimensional space. We can just traverse our latent space to go from one point to the other. And we can see how a 1 becomes a 2 by first adding something at the top and the bottom, and then kind of slightly tilting the middle line. And this is also, you can observe it on the right here. So we again have our 2 latent space variables. And on the one side, left bottom, you have something that is kind of a circle. And on the opposite corner, you have something that is very straight. So like a 7, which has 1 straight line down and 1 straight line at the top. And moving along that axis, you can see that the axis 1 here, on when you go up and down, if I can point it out. So when you're moving on this axis, you can see how a 0 slowly becomes something that looks like a 6 by just opening up that hole up here, and then over here, how you can make it thinner and thinner, and then it becomes something like a 1. The loss function for our variational autoencoder is pretty similar to what we have had before. So we again have our reconstruction loss. The only difference here is now we're having an expectation, because, as I said before, we're having a probability distribution now in the middle of our network. So we have to use the expectation here. And what we can see on the right-hand side here is a second term, which we'll discuss in a minute, a regularization term that helps us to make sure that our probability distribution in our latent space has a certain shape. More precisely, it should be a normal distribution with center 0 and variation 1. And this is what we're doing here in the second part of our loss function. One practical issue that we have with variational autoencoders is that we have some sort of randomness in our network. So again, we predict mu, we predict sigma, and then we sample from that probability distribution. Now, when you think about the backpropagation step, what would be the correct backpropagation method for randomness, for sampling of that probability distribution? So it's super hard, and this would actually break our system. So what we can do is, instead of sampling from mu and sigma, that we split the part that we train and that we learn from that randomness. And how we do this is that instead of sampling from the probability distribution with center mu and variation sigma, we sample from a standard normal distribution, 0, 1, and then we multiply it with our variation and add our mu. So we kind of split it up, and that z that we're having here, where we're sampling from, this thing is not to be trained, because it's just sampling from a standard normal distribution. It doesn't need any parameters, it doesn't need anything, so we can actually ignore that part during backpropagation, and we can only then use that sampled value to compute the value in our neural network, and we can kind of split it into the parts that we can train and have to train, mu and sigma, from the part that contains some randomness that we now don't have to train. And by doing this reparameterization trick, we can actually learn and train variational autoencoders. The second term that we saw before is an interesting thing. It's the so-called Kullback-Leibler divergence. And what it does is it measures the divergence between two probability distributions. So it's a slight modification of our formula for the entropy loss that we saw before, but rather than just having our probability distribution P, we add in our approximation of the second probability distribution Q here, and then we take a look at the difference of the log values here. So we're kind of trying to calculate how much information we're losing when we're approximating one distribution with another distribution. So we're kind of doing a similarity thing here, but with distributions. That's why this Kullback-Leibler divergence is super important and super interesting to study. Intuitively, this loss encourages the encoder to distribute all encodings for kind of all our inputs evenly around the center of a latent space. If we say Kullback-Leibler divergence with this normal distribution 0, 1. And now if the network tries to cheat and cluster the things far apart into specific regions away from the origin, it will be penalized by this term. So what we get is this beautiful thing here on the right side, where we have our mu and sigma kind of being regularized to that center here in the middle. So when we take a look at an example of this Kullback-Leibler divergence, we have some observed values from an observed distribution, and we compare it to two different other distributions. In this case, a uniform distribution and a binomial distribution. And when you take a look at the data, we might tend to say, okay, it rather looks like a binomial distribution than a uniform distribution. Well, then let's actually put in the numbers. So when we say we take that divergence between these two distributions, we get a somewhat surprising outcome, namely that the divergence between the observed distribution and the uniform distribution is 0.338, whereas the divergence between the observed distribution and the binomial distribution is actually 0.477, which is higher. So we would actually be rather better off here just sticking to the uniform distribution than using this binomial distribution here. And one last thing I should definitely mention here, be careful with this. The Kullback-Leibler divergence is not a distance function because it's not symmetric. You always have one distribution and the second, given the second distribution, this here, so make sure that you don't misuse it sort of as a distance between two probability functions.
If you do want to measure the distance between two distributions, what you can use is the so-called Wasserstein distance. It also is known as the Earth mover's distance, and what it does is it measures the costs for transforming one distribution into another. So the image that you have below here is, think of it, you have like one pile of dirt and you want to move it to another place to have kind of this other pile of dirt. And what you do with the Wasserstein distance is that you kind of think about all different plans, how you can transform one distribution into the other, and then you try to find the optimal plan for moving this, and the costs that occur, so the mass that you have to move and times the distance of how much you need to move it, this would be the Wasserstein distance. And the useful properties of it is that it does provide a meaningful gradient that you can actually train on. So you will see the Wasserstein distance appear in quite a couple of architectures. As opposed to the Kullback-Leibler divergence, we can use it in both directions because it's symmetric. It's just the distance between two distributions. And it can be used even if the support of the distributions do not overlap.
There is a slight, a really nice spin on these variational autoencoders, so-called Beta-Variational Autoencoders. And the idea behind these autoencoders is that you want variables in the latent space to be interpretable. You want them to kind of reflect one single property of our input space. So ideally, they're independent from other factors, and then we would call this disentangled. If we don't use beta-variation autoencoders, we might end up with a latent space representation that is entangled. So when you change one variable, you might have different kind of property changes in the output at the same time. But when we use beta-variation autoencoders, what we're doing is we're adding a factor here, this beta factor, onto the second part of our loss function here. And what that does is it allows the network to disentangle our latent space representation. And if we disentangle different features in our latent space representation, what we can do is now interpret those variables. And the images on the right side that you see here is that obviously the first latent space variable that this neural network learned was something like the head pose. So you see whenever you change that value, it kind of turns to the left or to the right. It also does that somewhat in standard variation autoencoders, but not as clear as in beta-variation autoencoders. Maybe another thing would be how much a person smiles or some other features that we can see here. And changing that one value now in our beta-variation autoencoder allows us to interpolate and interpret certain variables here along the way. Let's take a look at variation autoencoders in Keras. We're now in Keras, and what we have here is a small example of our MNIST, our famous MNIST dataset of how we can use variation autoencoders here. And let's start with the network so we can actually see this in action. We have our input here that has a certain input shape, and then we use a very small network that has two convolutional layers here with some activation function, and we do the following. So at the end here we flatten that and we use the last output here after we flatten that into 16 neurons and produce two outputs. So from that X we produce Z mean and Z the variation here. So those are two things that it has to learn, and we're representing each of these with a certain number of neurons that are specified in this variable. So our latent dimensionality is 2. So we have a two-dimensional latent representation for Z mean and the variation here. And what we now do is we have our lambda that is now the reparameterization trick in action. So we take this sampling. Now let's take a look at the sampling method at the top here. So we provided some values, which is the mean and the variance. And we sample from, so there's the random normal distribution here. And then we actually compute this. So we say our epsilon times our variation plus our mean. And that is what we want to have here. Variance, sorry, not variation, variance. So that gives us our Z, and that is the final encoder. So those three values will be in the output of our encoder. And when we run this, we see that there you go. So we have all of these things here in the output, and it doesn't contain any randomness because that is part of this lambda function here where we sample. So we disentangle them, and now we do this the other way around. We have our decoder, which is again taking the latent thing as input here, so the latent inputs, there you go. We put it through a dense layer and then we reshape it we use these inverse convolutional layers that are upscaling. That again, here they're called conv2D transpose. And what they're doing is they're now upscaling this again, and we end up with our output that has a certain dimensionality, as you can see here. So we had a 3136 dimensional output. We reshaped that into 7 by 7 by 64, and our transposed convolutions upscaled it to what we have in the end is a 28 by 28 by 1 output, which is again our input dimensionality for our digits. Our reconstruction loss is now, for example, the mean squared error. And then we can actually compute the loss here and train this thing. Let's take a look at what happens here. So we're training, and at the end we get this nice visualization here. So we can see where the network put certain inputs, and the color indicates our classes in our latent space representation. And the good thing is that given this two-dimensional latent space representation, we can actually just print it in this nice little graph. And we see an image that is very close to what we see in the slides just before, where the network learns something like zeros over here, like circles, and something very straight over here. And you can see that by moving along one axis, what that axis kind of changes. So maybe the axis 0 means whether it should be rather round or thin or something straight. So when you go from left to right, you can see it's getting more and more straighty. Yeah. So those are variational autoencoders in Keras. With variational autoencoders, or with autoencoders in general, we can do lots of cool things. One thing is what we've already seen in a previous lecture is image segmentation. And now I hope you understand what this image actually resembles. It's an autoencoder. So we have our input image, we do a bunch of convolutional layers, we have our latent space representation, and then deconvolutional layers, so we upscale it again. And the only difference that we have here is instead of predicting the input, we're now swapping it with the segmentation map. But the idea is pretty similar to an autoencoder. And what you can actually do here is that you can pre-train this with a standard autoencoder and then swap the output that it should predict with the segmentation mask. Therefore, you have some unsupervised pre-training. We'll see this again in a bunch of other examples. Another cool example would be that we can train an autoencoder to do noise removal. So a denoising autoencoder would be the following here. We have our standard, our clean input X, and there is a corruption process. Somewhere along the way, our signal, our clean signal X got corrupted and became this X tilde. And we have to specify this corruption process. So if we know what kind of corruption can happen along the way, we can just apply that corruption process to our clean input X. For example, when we take the number 2, we can add some noise to get this distorted sample, and then we train the remaining autoencoder as usual. So we learn the decoding of that noisy example and then reconstruct the kind of clean sample with the decoder. And the trick is now that we're computing the loss not between the noisy sample and the clean sample, but between the two clean samples. And if you put this into practice, then of course the real samples that you would gather in the field would then be this X tilde. So you probably don't have the real clean sample, but you can still use this denoising autoencoder then to be able to recover from any corruption process that you were able to model during training here. You can do similarity detection with autoencoders, where you just train an autoencoder, as we've seen before, and then we just throw away the decoder. Like, we don't need that anymore. We just need the embedding, the latent space that it learned. Now, in our latent space, what happens is we extract some features, and if objects in the latent space, so if we have this interpolatability between two classes, we can say, okay, they are probably going to be very close in the latent space. So if the distance in the latent space is very small, they are probably similar. If the space in this latent space representation, the distance, sorry, is big, they're probably dissimilar. The same idea we can almost identically reuse for anomaly detection. So we train our autoencoder in a standard way, and then we write down the largest loss that we saw on our validation set. So imagine that we have some input samples and we're getting a loss that is between 1 and 5. That's our typical loss that we see in our validation set, which is fine because we have a lossy encoding here anyway. And then we take that network, that train network, and just put it into production. So what it will do in production, it will take any input sample and produce a certain loss. And if that particular loss that we're seeing in production is now much greater than the biggest validation loss that we saw when we trained this thing, there is an anomaly, because it clearly is out of the distribution that it expected to see that it saw during the training phase. We can use it for semi-supervised pre-training, where we train an autoencoder in an unsupervised way, because when we just train an autoencoder, we just need inputs. We don't need any target labels. So we can kind of pre-train, even for image classification, we can train such an autoencoder for some time. And then we throw away the decoder and replace the network, kind of the decoder, with another network that produces our desired output. That then would be supervised. And we can optionally train this new decoder as well to have kind of this new output and the decoder, or we can just throw it away entirely and just use the encoder for getting a good representation of our input features. This way of doing semi-supervised pre-training is especially helpful if you only have a few samples for which you have annotations. Imagine that you have, say, images of X-ray images of your chest, of your lung, sorry. Then it's easy to get a lot of samples of these because they're being produced on a regular basis in the hospital. However, it's much harder to get samples where a doctor found some issues in those images and annotated them. So what you can do is now you take an abundance of unlabeled data of just X-ray scans of the lung, and then once you are able to extract good features that you pre-trained with this autoencoder, we can replace this and do our actual classification, for which we then only need fewer examples. A similar yet different idea is to have the desired output directly in this latent space representation. So instead of producing it in the output, we actually have it in the center of our autoencoder. We would then call it pi. And some people propose this kind of one network to rule them all, where you can say, okay, I'm using only certain parts or everything to do the desired task that I want. So let's start with the thing in the middle. We have our inputs, and then we produce our pi, our target classification. This is what we've already seen before. So we don't have any decoder, we deactivate the prediction of mu, sigma, and so on. We can also do the thing at the very right, which would be unsupervised, where we don't have this classification in the center. And then we can actually have both of them, this semi-supervised thing where we can help the network to do a better job at classification by giving it assistance and more information by running this full autoencoder and reconstructing the input. And you can actually, if you have this neural network, if you use the left one, you can change between different modes. So you take the same network, but you just deactivate the classifier, and then you can just run unsupervised pre-training. Then you switch on that prediction part for the classifier, and you can continue training in this semi-supervised fashion. This is a super exciting idea that I saw on a conference last year, that we can use autoencoders to basically learn an arbitrary encoding or decoding by fixing one side and just train the other side. So the idea would be the following. The task was to take an audio sample and kind of produce something in the middle. So a standard autoencoder would go from this audio to something in the middle and then go back to audio, because we want to reproduce the same input. So instead of producing something in the middle, which we can't really interpret, we actually want to have something more specific. And we can say, okay, our decoder is, instead of something that is trainable, we can use a non-trainable decoder that will always produce something depending on what comes as input. And if we have the audio domain as synthesizer, it will create audio samples. So we want, for example, to be able to recognize kicks and snare drums of your bass or of your drum recording, or closed and open hi-hat. And that synthesizer, if you feed it certain inputs, will produce that sample. So that something in the middle here becomes now the drum transcription. So we're actually now learning how to encode audio into the appropriate drum transcription in an unsupervised way. Do you see why this is so cool? We don't have to label our audio. We just say, okay, we do this in autoencoder, but the decoder is fixed. It's a synthesizer. It always creates samples. So the network has to learn how to fiddle with that synthesizer to produce the correct audio samples. And it only is able to do this by learning the drum transcription, because that is what the synthesizer requires as input to be able to produce the correct audio. And this thing works, and I think it's a super exciting idea, because you can come up with many other ideas where you fix one part here, either the decoder or the encoder, and then be able to train like a certain task in an unsupervised way. And unsupervised learning is always better because you can just use unlabeled data. And usually for many problems we have lots of unlabeled data and only have annotations for a small subset of them. So I think that idea is really exciting, and I think there will be many follow-up works that employ similar ideas in the future. We can also use autoencoders for generating new samples. So we train our autoencoder and then we throw away the left part. We throw away the encoder and just feed noise into our decoder. And the decoder has learned to take something and produce samples that resemble our input. So it will produce samples that are from our input distribution, and that is how we can build a generator in a really nice way.
And I'm talking, of course, about diffusion and diffusion models. Diffusion models learn a complex function that transform a simple distribution sample, basically Gaussian noise, into a complex one, into some actual data. So how do they do this? The idea is the following. Think about our original data. We have, say, a sample, an image of a cat. Now we can add some Gaussian noise here to corrupt the data sample. And then we'll have like a little bit of a noisy data sample. And this process here can be repeated. I mean, of course, like we can add more noise and we can add more and more and more until eventually the sample that we had becomes indistinguishable from just random Gaussian noise. Now, what diffusion models do is they actually learn to reverse this process. And we've seen this before with variational autoencoders that can learn to denoise a sample. So you can basically think of it as having variational autoencoders that would just chain together. And then you have, say, t time steps. And for each time step t, you learn kind of how to remove a little bit of noise until you eventually end up with a pipeline that goes from complete noise into a clean data sample. This uses the same reparameterization trick that we've talked before. And the powerful part here is that actually instead of learning, say, 10 different neural networks, we're just learning one neural network that can repeatedly feed the same data sample into itself. And this works because we basically have two underlying assumptions for these diffusion models, which are the fact that we assume the dimensions are the same in each time step, such that we can feed it in over and over again. And all encoder transitions are known Gaussians centered around their previous input. I've linked two resources here where you can learn more about the math behind it and how that actually really works. But for the sake of time, I'm just giving you a couple of examples here what you can actually do with these diffusion models. So they basically are really powerful at generating samples from conditional distributions. So we can take random Gaussian noise and have our autoencoder pipeline here that is conditioned, for example, on class labels. And then you can take kind of the right part here and say, give me an image of a cat, input some random Gaussian noise and this class label, and it would generate a picture of a cat. Similarly, you can create images out of textual descriptions, basically having text-to-image models, or you can even have a diffusion model that can upscale images, that is conditioned on low resolution images and then produces much higher resolution images.
We can use that idea of generators and take one step up and do something that is called generative adversarial networks, which is an extension of this idea, and it also feeds into what we've seen last week with reinforcement learning. So, what are generative adversarial networks? Given some training data, we want to generate new samples of the same distribution. All right, so we have images of cats and dogs and planes, and we want to produce, again, images that resemble cats and dogs and planes. So what we can do is we take random noise, we have our generator, for example, the one that we saw previously from this autoencoder scheme, and then we get a sample from our input probability distribution. So the question is how to train this. One way obviously is now by using autoencoders, but there's also another way that is really interesting. The idea is that we use a game theoretical scenario of two opposing sides, where we have one side who is the generator and one side who is the adversary, the opponent. And what they're doing is they're playing against each other. So we're not modeling an explicit density function. What we're doing is that we're having a generator that generates samples that look like the data obtained from the training set. And it tries to fool the discriminator. It tries to produce samples that look as realistic as possible. And then the discriminator on the other side is doing the inspection and says, well, that sample is definitely from a different distribution. So you have this generator that tries to come up with samples that look as realistic as possible, and the discriminator who tries as hard as it possibly can to be able to distinguish between real samples and fake samples that were generated. And by letting those two opponents play against each other, we can train a neural network to do some really cool stuff. So how does this work? We train these two networks, these two sub-networks, in a joint min-max game. So we're alternating between the two. We're taking a few training steps for the generator and then taking a few training steps in the discriminator. So we train the discriminator with gradient ascent and the generator with gradient descent to be able to produce good examples. The problem now is when we use this training scheme that the discriminator or the generator would receive a very low gradient signal from the discriminator if it's doing a bad job. You know, it will take some random noise, and if it's doing a bad job, it creates just some random shitty samples that do not resemble our real distribution. So the discriminator will have a super easy job at figuring out whether this is real or not. And so the loss that gets fed back to the generator now is very low. Whereas if the generator is already doing a really good job and those samples are very realistic, the discriminator will be fooled, so the signal will be high, the gradient signal that we receive back. I hope you can see the problem that we rather have a high signal when it's doing a bad job and a low signal when it's doing a good job. We're getting the same thing. That's why we reformulate this problem here in such a way that we also use gradient ascent on the generator. And in other words, we're minimizing the likelihood of the discriminator. So when we do gradient descent here, we're minimizing the likelihood of the discriminator being correct. But instead of that, we would like to maximize the likelihood of the discriminator being wrong. So we want the discriminator to be as wrong as possible for the generator. One thing to say here is that in general, training these two things can be very tricky because it's a bit unstable. You know, there is a balance between these two. If the discriminator is too good, then the generator has no chance on learning anything. If the generator never picks up on something realistic, then we also won't see anything useful here. So how can we train a GAN? We take a number of training iterations and we sample some noise from our noise distribution. We use our data generator distribution, and then we update our discriminator by ascending its stochastic gradient. So that part here, for a certain number of steps, we are training our discriminator. So the generator is now fixed and we are training only the discriminator. And then we do the second part where we sample some noise from our distribution and then update the generator by also ascending its stochastic gradient. However, there is no clear rule yet how long you should train each of these two things. How long you should train the discriminator, how long you should train the generator. Let's take a look at how this generative adversarial network looks like in code. Okay, we're back in our code here, and let's take a look at what's going on here. So we're setting things up a little bit. We're loading our famous MNIST dataset. Well, thanks, we have them. And now let's take a look at the neural network. So we have our generator, and that generator takes some input. process them in a multi-layer perceptron fashion. So we have a bunch of fully connected layers, and then we produce a certain output here, and the discriminator goes the other way around. So it takes that large sample and kind of tries to do a classification of that again. So in the end, it has a one-dimensional output, with whether it's now fake or real. And the idea would be then that that single value is the probability. So if it's kind of positive or negative, it's rather fake or not. So we interpret this in a certain way, this one value. Now the training function is, there is a gradient penalty that I won't go into detail now, but training one step now looks the following. We take this discriminator and we feed it some real samples. So we are able to compute the loss on some real samples. We're also feeding some fake samples through our discriminator. We could mix and match them, but it doesn't matter because we're just computing stuff here. And then we're backpropagating our gradients. This is the additional step here. And then we can also train our generator here. There is some data preprocessing, and then there is the training. And now we can start the training, and what you can see here is really interesting. So those are those are the generated samples at the beginning. So what you saw just before was the first few samples that the generator produced, which were just noise because it didn't know anything. And then we start the training here. And over time, we can see out of these samples that it generates, it starts to kind of look more of what we have in our actual output distribution. So it's not yet an actual digit, but we see the discriminator now becomes better over time. So it learns how to discriminate between real and fake samples, which is good initially. And then we have our generator that produces some things that, well, the loss goes up in the beginning because it's still learning how to do this. And at the same time, while this thing now goes up, it's also understandable why the loss goes up for the generator, because the discriminator got better. So at the beginning, it was just producing something and the discriminator didn't have any clue how fake examples looked like. So as soon as the discriminator got to a lower loss and learned how to distinguish between real and fake examples, the loss for the generator went up. And that makes sense because now it was the generator's turn to learn something useful. And over time, what we can see now is that that loss of the generator should go back down. And I think we're actually seeing this. So this now tends to go up, or I mean, it should stay down, the discriminator loss. Ultimately, if the generator becomes good enough on fooling the discriminator, that loss here will go back up and the generator loss will go down, down until it's all the way down. Okay, I just made a short time lapse and we're at the end of the training. And what you can see here now is the final trained discriminator and generator. And as you can see here, the curves have made the desired form. So in the end, the discriminator turned out to be poor. So the generator did such a great job that the discriminator could no longer distinguish between digits or that were generated by the generator or actual digits from the original distribution. And the interesting thing is we can take a look at how this evolved over time now by changing the sliders. So initially we started off with noise. So at step 0, all we were generating was noise. And then in the first few steps, the first few thousand steps, you saw or you can see that it evolved into something that resembles a 0. So that was the first thing that the generator learned, to do something that looks like a 0, and that already brought it to like somewhat good results. So it was able to fool the discriminator to detect this as a 0, and then over time, as you can see, it started to learn more and more shapes. So what we can see here slowly starts to resemble digits as we would expect them. So, and at the end here, hopefully they look like something that we would classify as certain digits, like 5, 0, 8, well, 4, 9, whatever, 3, 2. So those are now digits that I think look pretty good, given that it learned this by just trying to fool the discriminator. One question that you might have at this point is, how good is my GAN doing, and how do I know whether it's doing fine or not? Especially when you consider that there are some competitions where you have different teams that are creating their own generative networks and generate some really nice samples. How can you have some kind of objective measurement for them? One thing that we could do, obviously, is we could take a bunch of images, both generated and real images, and show them to humans and let them classify them. Say, okay, tell me, is this a real image or is it a generated one? But as you can tell, this is of course prohibitively expensive, and of course it cannot be automated at all. So it's not a good fit for competitions. However, there is a very popular alternative that is used nowadays, which is called the memorization informed Fréchet inception distance. Yeah, it's quite a mouthful to speak, but what it is it's a single numerical evaluation, which is exactly the kind of thing that we want to have, which compares real samples with generated samples in a pretty objective way. And it is actually an evolution of several previous metrics. And in order to understand this, I'm going to break it down from the back to the front. So let's start with the inception distance. The inception distance is also called inception score, and instead of manually classifying the images, we're just using something that we've already invented, a neural network that does the exact same thing for us. So we take 30,000 generated images, we classify them with a pre-trained inception v3 network, and then we take a look at two different measurements here. One is the entropy, and the other thing is the distribution across all possible labels. And the entropy here, we would like to have a low entropy, and if we have a low entropy, we would get a high score. What does it mean, the entropy here? We basically want the network to always have a single, distinct, kind of clear output prediction, which you could think of as answering the question, how sharp are images, or how distinct? If it's always very clear that it's a dog or an airplane, then we have a low entropy here, and the network kind of produces sharp images. And the second one is we want to have this kind of even distribution. We don't want the network to be unfair or only produce things of just one kind. We actually want the model to produce kind of all classes that are possible to generate. One problem that we have with the inception score here is that it only evaluates the generated images and doesn't take the similarity to real images into account at all. So we're just taking a look at the generated images, which is nice, but I think we can do better. Which brings us to the Fréchet inception distance. So this is the kind of next version of this, if you will. So it expands on the inception score by comparing the generated images with actual real images from our distribution. So you take a large number of samples, generated, real, you run them through the inception network, but without the final classification layer. So we kind of stop one layer before, where we have our 2048 dimensional activations, and then we compute the Fréchet distance between these two distributions. One quick question: why don't we take the final classification here? Well, the layers that are close to the output node are of a higher dimensionality, so they generally contain more information than if we just have 10 output classes, those 10-dimensional things. And of course, we don't take the raw inputs because they don't kind of correspond to the features or to like real objects that we want to have. Now back to the Fréchet inception distance. The Fréchet distance itself is a measurement of similarity between two curves, and you can think of it as the following. Imagine a person is walking with a dog on a leash, and they're walking together from A to B, but they're not walking at the exact same speed or the exact same way. Now the question is, so the dog is maybe moving forward, then a bit to the side, etc. What is the minimum length of the leash that is required while these two go from A to B? And this minimum length of the leash between the two, the man and the dog, or the person and the dog walking from A to B, this is what the Fréchet distance is measuring between these two curves of the path that they are walking. Now, this is already a big improvement, as it kind of allows us to compare with real images. However, there is one problem. What happens if the generator just starts to memorize the training set and produce images that are kind of like just the actual real images that it saw during training? And this is a real problem, and brings us to the last one here, the so-called memory-informed Fréchet inception distance. The kind of underlying reasoning here is that the authors ran a competition, and they figured out that there is a high, kind of a strong correlation between the memorization distance and the Fréchet inception distance. Meaning that, of course, people that produce the training data or something that is very similar to it as their generated data will also kind of score here well in these competitions. But we don't want that. We don't want the generator to just reproduce the training data. We want it to come up with something new. So they penalize the network for memorization of the training set. Meaning you calculate the Fréchet inception distance as before, but you add this memorization penalty, which is the average minimum cosine distance between the features of the real and the fake distribution. And again, this is a single metric that you can compute, and it just additionally makes sure that you don't kind of incentivize people for reproducing the training data. Now let's have a look at a couple of really cool applications with generative adversarial networks. You can use this for style and domain transfer, which has been shown that it works amazingly good, where you can take any natural photograph and transfer the style into some of those famous painters like Monet or Van Gogh, and kind of generate images that look as if they were painted by Van Gogh, which is fantastic in my opinion. And there are many, many, many more applications for autoencoders. There is even, especially for generative adversarial networks, there is a so-called GAN zoo. So please check out this resource if you have time. There are hundreds of examples of excellent research that has been done to kind of get from an aerial map to kind of a street map, or take an image and transform day to night or night to day or summer to winter, and some amazing photos that they produced or recolor old footage that we only were able to have restored in black and white. So there are some fantastic works here, and I'm pretty sure the future will bring even better examples of what we can do with these GANs in particular. Summing up our lecture today, autoencoders can do unsupervised learning, which is cool because we need less annotated data, which is always tedious to obtain, and usually it's much easier to gather a large data set that is not annotated than having to manually annotate them. And by carefully selecting the objective function, we can enforce certain properties in our latent space. So we can make it interpretable, we can make sure that their variables are disentangled, and we can use them now kind of as sliders to turn certain features up or down. Variational autoencoders are a probabilistic spin on autoencoders where we produce not just a single layer in the middle of our hidden representation, but a probability distribution that we sample from, which again gives us some really nice properties and also helps the decoder to become more robust to slight variations. And then we saw generative adversarial networks that are another way to generate new data by having this game theoretical idea of two opponents where we have this generator and the discriminator, and they're playing against each other. And it's a very active area of research, and we're seeing some new things coming up every year, probably even every month, like conditional GANs, Wasserstein GANs. So there are lots of new things that will come into future. So keep looking out for these exciting new research areas. And with that being said, I wish you a wonderful day.